think I'll just go ahead and start. Does that sound like something to do? Okay, I think I'm going to go ahead and start. And so I am going to talk to you about a new experiment. It is an experiment which is called IsoDAR. And I'm promising you something completely different. So we'll see if by the end of this, I have convinced you that that is true. So I want to start out by playing a game with you, okay? I'm going to put forward a premise. My premise is that you have a job, and your job is to pair a powerful accelerator with an ultra-large detector to open up new neutrino physics. And I want you to do this in a realistic way. So I have some rules of this game, okay? You are going to have to do this by, first of all, sticking with the basic premise above. You can't decide, oh, I'm going to axe the accelerator, or oh, I'm going to axe the large detector. You have to stick with the basic premise that you see right here. You can do other physics than neutrino physics, but it should also do neutrino physics, okay? So that's part one of the game. Part two is that I don't want you to just pick up something that exists and try to somehow shove it into someplace, right? I want you to think through what really belongs together in this scenario. And then lastly, I want to have something which fits into what's called the P5 ASTI program. So does everybody here know what P5 is? The panel that sort of sets priorities and projects in particle physics. And one of the big changes that they did in the last P5 was they set up a new scale of projects, 50 million and less, and they called it the Agile program, and the A in ASTI stands for Agile. So it should be an experiment which the whole thing can be done for $50 million, okay, or less, hopefully less. All right, you have five seconds to think about this. See if the clock goes. Oh, the clock might be stuck. Okay, that's it, folks. Okay, I want to say that there has been a group of us who've been thinking a lot about this for a long time. So it's a little hard, I think, to compete, although I'm perfectly happy to listen to what it is that you all have to say here. So let's start out with the ultra-large detector. Okay, there's many ultra-large detectors in this world. Super K is an example. There's many all around. And most of them are designed to look at low energy events. Say less than 20 MeV. Because of this, because they want to see these low energy events, they are built deep underground to reduce backgrounds from cosmic muons. They can't escape environmental backgrounds, though. It turns out that the dust around you, the rock around you, has a lot of emissions. And these emissions are all happening below about 3 MeV. So there's this environmental background region below 3 MeV. So what do we want then for my pretend experiment, for our premise? We want to have something which produces a relatively high energy beam compared to this. So let's decide that we're going to use an isotope to get this relatively high energy beam. You would like to find a very high Q value isotope. But high Q value means short lifetime, at least for beta decays. So as a result, that means you're going to have to continuously make it. However, if you choose something like lithium-8, you really get a very nice, relatively high flux, energy flux for the neutrinos. And so lithium-8 is a really nice example of something that you could use to try to address this problem. Okay, so that's great. Lithium-8 has a Q value of about 16. It has an 800 millisecond lifetime. It produces pure nu E bar. But because of this very short lifetime, you're going to have to make it, okay? But it turns out it's not that hard to make. The way that you make lithium-8 is you make lithium-7, which is a stable isotope, with neutrons. It'll capture the neutrons, become lithium-8. And so then you get your decays. So that means I need neutrons. So how do I get my neutrons? Well, one way to get neutrons is to run protons into a beryllium target. That is a tried and true method for getting your neutrons. You're releasing the 1.7 MeV neutron, that's the least attached neutron, and the beryllium, you're boiling it off essentially, or spalating it off. And then the lithium-7 will, when these neutrons go into the lithium-7, it will moderate the neutrons. It'll slow them down to the point where they can capture. So what you want to do is you want to then, and you want to get as many neutrons as you can into your lithium, right? So if you have fast neutrons coming into lithium that also has beryllium in it, then what can happen is you can continue to knock out neutrons in inelastic interactions, get more neutrons, those moderate, and you can capture as much as possible in your, by your lithium-7. And so that tells you then that you want to have an accelerator that's going to produce a lot of neutrons. And so here is world data on neutron production as a function of energy. Along this axis is the neutrons per proton on target. This is mostly beryllium targets, not 100%. And what you see is that on a log-log plot, this is rising linearly on the log-log plot. That might make you think, oh yeah, I want to be really, really high up in energy, but there's some issues associated with that. So let's talk about that. You're going to need an accelerator. And so what accelerator do you want to have? Well, you know, if you wanted to be way up here where your rates were very, very high, you're talking about an S&S scale accelerator. You are not going to fit within my original rules, which are that the whole thing is being built for $50 million or less, okay? If you can then choose an accelerator that you are going to build. One option is that you could choose a LINAC. A LINAC is a beautiful accelerator. It is also a very expensive accelerator. It is expensive to construct. It is expensive to run. And if you want to match up to an existing ultra-large detector, which is the only way you're going to fit this into $50 million, is to start with something like that that exists, then you're going to have to go ahead and build it underground. And superconducting underground is a pain, right? It can be done, but it is a pain. So you would like to avoid that. So LINACs are out. I like to say that LINACs are too nice. Okay. There are other kinds of accelerators like FFAs and DT generators. The DT generator scale is down here. So you need, if you're at low energies, a really, really high production rate for your DT generator to make up for the fact that you just don't get that many neutrons per proton, or you don't get that high rate for the DT generator scales. So these are not nice enough. These were way too nice for our use, too expensive. So what we end up with is we end up with choosing a 60 MeV, 10 milliamp compact cyclotron. I would argue that for this premise that I was putting forward to you, this is the Goldilocks choice, the one that sits right in the middle. But it's going to require some innovation. So I'm going to have to argue to you that we can actually do this. Okay. So, oops, sorry. So that brings us to our completely different experiment then. What we have is we have a cyclotron here. It is producing a beam of protons that's coming along here to a target. That's going to produce our neutrons that bathe a bubble that you see right in here. That's your bubble of lithium. We call it a sleeve of lithium surrounding it. And the anti-electron neutrinos come out next to a large detector. All right? So that's the concept here. So I want to now convince you that I haven't overstated things, that this is actually something that is really, really different and deserves your attention to actually really think. Okay? So I want to start out and talk about why this design is different from an experimentalist point of view, a particle physics experimentalist point of view, because that's really what I am. I'm pretending sometimes to be an accelerator physicist, but I'm not really a card-carrying one. So let's start with the particle physics experimentalists. And let's actually talk about a realistic description of the plan, okay? There is a new laboratory which is being built in Korea. It is being built at a place called Yemilab. And there they are already planning, they are funded to install a 2.5 kiloton ultra-large detector. And so this is a place where you have a deep underground system. It's about 1 kilometer underground. It has drive-in entry from above. This is the very windy path that gets you down to the lab. It has low sodium rock, which is very, very nice if you're going to put in an accelerator that's going to produce neutrons. You would like to do as low activation as possible. And it is a new laboratory. And the beauty of a new laboratory is that if you're going to try to do something which is a completely new accelerator, you would really like to have them build custom-made housing for it. And that was what they were able to do. They have built the caverns that we need for this. And some of you may be familiar with the Amore experiment. Some of you may have heard of cosine also. That's actually happening over here in the laboratory, and here's where the large detector goes and where our accelerator will go. So again, the concept, what we need to do is we need to produce ions that we accelerate. And so what we're going to do is we're going to begin with H2 plus ions instead of protons, even though we ultimately want a proton beam. But you can get a proton beam from H2 plus because you have two protons stuck together with an electron. So you need to just strip off the electron after you have accelerated this ion. I'll talk a bit more about why this solves many problems later, but I just want to introduce now, when I talk about an H2 plus machine, why I'm saying that. So then it gets accelerated in the cyclotron. It gets brought over to this target, as I told you about. The neutrons are being produced by the target and multiplied in the sleeve you see here and going into the detector. The detector used to be called, up until 1 week ago, it was called the LSC, the liquid scintillation counter. And they decided that that wasn't a clever enough name, so they have changed its name to New Eye. And so now throughout this talk, I have to remember to say New Eye. But if I say LSC, I want you to know what it is I'm talking about. Okay?
That's not included in your 50
This is
million
not included in the talk because it was already going to be built. It's funded by the Koreans. So yeah, so part of the premise is to go find some of the materials that you need, right? Including the underground laboratory and all of that. All right, so it is a very classic kind of ultra-large detector. It has an outer veto. You always have a buffer region between the outer veto because the photomultiplier tubes will actually produce light if you put them directly into simulator. And then it has the target region, which is what I call the fiducial volume for the rest of the talk. Okay, so we have developed a design, and that is basically what the design is. I want to start by introducing you to what this design can actually do. So this is IsoDAR by the numbers first. And the very first premise that we wanted to have beyond the list of rules that I gave you for the game was that we wanted to actually have this be something where from the time that they said go, you can really start building this, until the time that we finished taking data, that we were within normal lifetimes of a graduate student, okay? So we are arranging for, we've set up all of our results that we're going to show you for a 5 calendar year run, okay, which I call one graduate student lifetime. And you can't run an accelerator all of the time. So we have 80% uptime for the cyclotron. And in the end, per year, we are producing more than a mole of protons onto the target. Okay, it is a very hot accelerator. What that does is that bathes the lithium-7 to make the lithium-8 and produces about, over the 5 years, about a mole of anti-electron neutrinos. You're getting at the level where you could actually gather them all and weigh them in principle to find out their mass. So I want to point out that this is a very, very large detector, which is part of what makes this so nice. Some of the physics that I'm very interested in is physics where there's a change in the physical process as a function of distance traveled by the neutrino. And this gives me a very long, continuously measured information on what happens as the neutrinos move along and interact. It's also, as I said, 2.5 kilotons, so it's a very large detector. So it's really, I think, a very pretty experiment from the point of view of what it is that you can actually produce with us. I can also talk about IsoDAR by the fluxes. Now, I've already told you that our anti-neutrino flux, that was part of our premise that we had to be able to produce, that anti-neutrino flux, you see right here, it's relatively high for one that's produced by an isotope. It's a single isotope, so that makes it really nice. But actually, there are 2 other fluxes that you can think about if you are an experimentalist or a theorist in particle physics. One of them is the photon spectrum that you get, and the other is the neutrons at production. Now, in both of these cases, the goal is to contain these particles. Don't let those particles go into your ultra-large detector. So, we absorb as many neutrons as we possibly can before we get them into the shielding. All the photons are getting absorbed. But if what happens is that those particles mix with some beyond standard model particle before they are actually captured and absorbed, then in fact, you can actually produce a particle that could move into the new eye and actually see new physics from it. So in fact, we think these are very interesting spectra also, and especially we like this photon spectrum, because the photon spectrum is coming from exciting the nuclei within the target and sleeve region. So what happens is you get monoenergetic production of those photons. And let's face it, all experimentalists love a peak, right? Okay, so let me go through these a little bit more about why these are so nice. You might have said, oh, actually what you really, really want is not this low energy isotope produced flux. You want a much higher flux because the cross section for neutrinos goes up as you go up in energy. So surely you want higher energy neutrinos, but that isn't true because it turns out that there are only a very few cross sections for neutrino physics that we actually understand very well at the 1 to 2% level or better. 2 of them are at very low energy, and the other one is called deep inelastic scattering, which happens at very high energy. So if you're an experimentalist and you really want to do precision physics to understand beyond standard model questions, then what you would really like is you would like one of 2 kinds of interactions to occur. And it turns out these are the only interactions that can occur when you're at these energies. The first is called inverse beta decay. So it has an anti-electron neutrino coming in, hitting a free proton in your hydrogenous detector, and out comes a positron and a neutron. The other is called elastic scattering. The anti-electron neutrino comes in and it hits the electrons in the detector. And these numbers of events, 2 million events in 5 years, 7,000 events in 5 years, which have all of the efficiencies on them, those are much, much higher than we have as any collected events in neutrino physics from any given experiment. So this flux is higher than those of reactors or today's sources, and it's not buried down where the environmental backgrounds are a problem. This single isotope decay is extremely well understood. Some of you may have heard some reactor talks where they talk about a 5 MeV bump that they don't know where it came from. You will not have that issue with this, okay? This is a very well understood isotope. And it's continuously produced at a constant rate. It doesn't just die off like if you put a source into your detector, but you can turn it off. So you can see what happens when it's off and when it's on. All right, so let's talk about why experimentalists love these 2 interactions that I was telling you about of the neutrino interactions. So let's first talk about the inverse beta decay. So with inverse beta decay, this cross-section is known to 0.2%. The reason why it's known so incredibly well is because this is just a refolded Feynman diagram, a twisted Feynman diagram from neutron decay, which has been very, very well measured. Experimentalists also love it because it is a 2-flash coincidence. You have the positron and then you have the neutron captured following it. It is very hard for backgrounds to produce something like that. There are very few candidate backgrounds out there. 2 that are well known because they come up in reactor experiments, which are not deep below ground, are lithium-9 and helium-8. They're produced by way of muon spallation in your simulator detector, but we're a kilometer underground. And so this is not a very big issue for us at all. It's negligible. And also there is another case where a fast neutron could come in. The fast neutron then scatters and then it comes to a stop and it captures to fake a signal. From the accelerator, we're designing our shielding for less than 5 events entering the fiducial volume per year. And for cosmics, we're deep underground using a muon veto. So in the end, all of this is very extremely low. The largest uncertainty that we have in inverse beta decay events comes from not knowing our efficiency perfectly well. Sometimes you miss this neutron. And when you miss that neutron, then you have to estimate how often it happens. And that has the largest systematic uncertainty at 0.7%. That is very, very good for a neutrino experiment. It is very hard for a neutrino experiment to do that well. All right, the other interaction is the elastic scattering interaction. This is a cross-section which is extremely well predicted. Again, now that we have found the Higgs boson, it's extremely well predicted if you think the standard model is the perfect model with nothing else added in. If you start adding things into the standard model, that will cause deviations from this cross-section. And in particular, it will cause deviations as a function of the energy that is observed in the detector, the energy that the scattered electron will have in your detector, from what I show you right here with this green line. And those deviations are very interesting. They can point to things like neutrino magnetic moments and other very interesting beyond standard model possibilities. But this is a single flash now. You only have your electron coming out. So you have to reduce background somehow. We're doing it by going to an underground location. There is enhanced purification in this system. It's going to be very similar to Borg-Sino in terms of purities. We are applying a 3 MeV cut applied to all analyses, and also type fiducial cuts to all analyses. And that's included in all the statistics that I show you. Nevertheless, we expect some backgrounds to get in. Here are the different backgrounds I'm showing you. Here are some of them up here. In fact, solar neutrino interactions are a background, which we cannot shield from. So you get a sense of where our backgrounds are. One of the things you can see is that the shape is different, but also it has very distinct peak structures, which we can pick out and try to use to understand exactly what the background is. Plus, we can just turn our accelerator off and measure these. All right. So experimentalists love those neutrino signals. Those are really great. Experimentalists also love a monoenergetic source. It's hard to come up with a monoenergetic source that we don't really appreciate. And this photon spectrum is a really good example of this. So it's coming from the resonances, as I told you. And so the peaks can be identified through bump hunts. And this is actually something that I've worked some with Bhaskar on, and so I'll show you some results later on in this talk. But what we're doing is you're looking for peaks in the analysis, peaks that disappear when you turn your beam off, for example. And so I think there's really interesting physics to be done there. And most physicists experimentalists do not love neutrons. There are a few neutron lovers out there. Those neutron lovers, you know, I'm sorry to say it this way, but the truth is most people don't love neutrons. So what are we doing about all those neutrons? Well, we are capturing most of our neutrons in the sleeve. We are also setting up our shielding so that most of the neutrons don't leak out. But nevertheless, that leaves us with a neutron flux at the very beginning. And just after the neutrons are produced, before they are captured, there is a time where the neutrons could actually mix with some kind of beyond standard model process. And that would allow us to have particles appear in our detector. And so I'll talk a little bit about that in a moment. I just want to say, this is why for an experimentalist, IsoDAR is unique and pretty exciting. We have extremely high fluxes neutrino interactions that are very well understood. We can also constrain many of these, especially by turning the accelerator off. And it's an opportunity to look for new particles coupling to neutrinos, photons, and neutrons in ways that have never been done before. And that is what is so exciting about this. This is not an incremental idea, okay? This is an idea that is so different that you can see things in a very, very different way. All right. So that is why I think the particle theorists in this room should appreciate this experiment. I had an interesting problem with this talk. I needed to talk to particle experimentalists, I need to talk to particle phenomenologists and theorists, and I need to talk to accelerator people too. So I think I've done a pretty good job, but we'll see what you think by the time I'm done with the talk. So let's talk to the particle theorists for a few minutes. This is what P5 has said describes particle physics and what is interesting in particle physics. I've left out a few things, but basically the large picture is decipher quantum realm, explore new paradigms in physics, and illuminate the hidden universe. And then underneath these are actually two things for each one of those, but we actually can address 4 out of 6 of those areas with this new experiment. So we can search for different kinds of properties of neutrinos. We can search for direct evidence of new kinds of particles. And we can look for effects that would really change how we understand cosmic evolution or dark matter. So I'd like to talk about these, and I'm not going to talk about all of them, but I'm going to briefly skim through just a subset of these. But I want to say that This is the list of what we've actually looked at, but I would really love to have people here who would be interested develop more ideas here, and we're really happy to give you the fluxes to think about this. So let's start by talking about new neutrino properties, because that's always been a love of mine. And in particular, there's a question of whether neutrinos behave as a function of distance as they travel along in the way that you actually expect based on our standard model, or a slightly extended standard model to explain the masses of the 3 light neutrinos. And actually there are models out there where there's quite different behavior as a function of this distance traveled, or usually we express it as a ratio of the distance traveled divided by the energy, which in some kind of units is basically time. It's change with time. And so what you see here is you see 3 different models of behaviors, which are really pretty dramatic when you realize that IsoDAR can make measurements with the error bars that I show you here. So you're looking at a continuous detector, you're looking at it with incredibly high statistics, and you can really tell, you would know if you had this model or this model or this model. And that's, I think, a really exciting thing that we have not been able to do when studying, for example, neutrino oscillations, but you could also talk about neutrino decay, other effects. We have little spots here, and we have little spots here, and little spots here where we make our measurements, but nothing continuous like this. Okay, we can also consider the other kind of interaction that I was talking about, elastic scattering. And what I said to you is the elastic scattering is extremely well understood as long as you believe the standard model is absolutely complete. But let's, for example, introduce some kind of an exchange particle which effectively changes the coupling of your electron-flavored neutrino to the electron. Then if that happened, what you would get is you would get a deviation from the standard model prediction. So this is the amount of deviation that would be observed from the standard model prediction, which sits at 0, 0. And people have looked for this. This is the region that is now open for exploration presently. Everything outside of it is excluded. And what IsoDAR can do is it can do something that is much, much more narrow. It's also tilted because this is largely neutrino interactions, and this is entirely anti-neutrino interactions. So there's a real differences between this. And this is a very interesting thing to look at. These are called non-standard interactions. And it complements a program that is a big program in the US right now, looking at coherent neutrino scattering, which is looking for lepton quark, new interactions between leptons and quarks. So I also said you could play around with the neutrons, right? And one person's particle that they don't love is another person's, true love. It turns out to be true for Matthias Hostert and company, who put together the following paper. The idea is that we produce a lot of neutrons here, and if those neutrons converted to, went into the dark sector, mixed with a dark sector particle, and then came back out, they can actually penetrate far into the detector. Now most neutrons can't penetrate very far in the detector if they make it to the detector at all, because it's a detector full of hydrogen. They immediately moderate and just die out. So getting to the fiducial volume is extremely hard, even if you made it all the way through our shape. But this is looking for a neutron that appears right in the middle of the detector and produces a nice 2.2 MeV gamma in the middle, which you would not expect to see. And so this shows you then, in terms of the mixing with the dark sector, and also the mass difference, where you would expect to see a signal for IsoDAR, which is shown like this. And this is interesting, not just to people who are particle physicists, but also to people who are interested in neutron star heating. So that's what's shown by the red that you see actually here. Now, I've been interested in something else, and it's something that I have not had time to look at, and I'm just going to throw it out here, and maybe that Bhaskar is going to tell me that this is a dumb idea. But something that I have really wondered about is if your neutron connects to something in the dark sector that is Majorana, then in principle, what you can get out actually is an N bar. And now I don't get 2.2 MeV out of this, I get 2 JeV out of this, kaboom, right in the middle of my detector, right? And I've had a graduate student look at what would come out in this. It's quite distinctive compared to, for example, a neutrino-neutral current interaction. And that has got to connect to the idea of the matter-antimatter asymmetry. So I just think this is fun. I would love to pursue it. I don't have enough time, but Bhaskar, if you wanted to work on it with me, I would try to find the time.
Question, on this, I mean, the neutron shining through the wall is much harder than photon shining through the wall, obviously, because neutron, you know, the non-Gaussian tails, they can make it through, or you might have gamma and neutron produced later in the shielding.
It has to go through 7 meters of shielding, and that's in the backward direction. So what we do with our neutrons is we actually bring our protons in, we bring them around and point them backwards away from where the detector is. So all the fast neutrons are going this way, where we have even more shielding. But between that and the detector is 7 meters of shielding. Then after that, we have a large hydrogenous veto. Then we have a large hydrogenous buffer region. And that is why we are very confident that we're going to make it down to 5 neutrons or less in the fiducial volume. And all of those are going to produce light only in that little region. If they haven't stopped already, they're stopping only there. So what he did in this was he actually cut out a lot of the region right where the accelerator is. So that's how you do it. We could also, if we wanted to, try there. I mean, we can turn down the intensity of the cyclotron. The way that you do that actually is you use a chopper. So it's instantaneously the same intensity, but integrated differently. Okay. So Bhaskar, I am pretty sure, thought that when I got to the photons, what I was going to do was show our axion paper. But I'm not. I'm not going to show that paper, even though I love that paper, because I love this even more. Okay? What I love about this is that this is the first experiment that is able to look for the following process. Oops. Oh, no. Here we go. The following process. You produce a rare particle which couples to the photon, okay? And that decays to a neutrino and an antineutrino. This is nothing decaying to 2 nothings, all right? But our detector is so large sitting there, and the signature is peaked because our photons are monoenergetic, right? You're only seeing half of it because the decay is 2-body, but it does go still monoenergetically in the 2-body decay, right? And so what happens is that you can actually see extra inverse beta decay events sticking up as peaks in your inverse beta decay sample, which I just think is really, really cool. So what you see here is, and this, by the way, was done with Adrienne Thompson. Do you all remember Adrienne Thompson? Yeah. And so the mass of this X particle is along here. Notice it fits within the atomic key anomaly. And also here is the ratio of the coupling of the decay up to the X as opposed to the decay to the gamma. And here you see where IsoDAR sensitivity lies. And in this plot, I show you no limits from any other experiment. And that is because this is the first experiment that could do something like this, ever. And I just love it. Now, it isn't the signal that a lot of theorists have thought about because basically people can't do it, so you just don't think about it, right? So it's truly blue sky. And I really want to encourage the theorists to think a little bit more about what we could do being able to do that. So theorists here at TAMU, what other completely new physics can IsoDAR explore? That's what I would like to know.
Can I ask, can you show the diagram of the accelerator and the detector again?
Go through more about the accelerator in detail now. That's what I'm about to go into. But here's the diagram.
Yeah.
So
okay.
you start out, oops, oh, damn it. Sorry. Here's my cyclotron.
Yeah, okay. So
It's very far upstream, but also cyclotrons don't get very activated. Is that your question?
no. So the point, so is the idea that you move the target or you move the detector?
Nothing moves.
Oh, it's just about
The
the,
detector is enormous.
okay, so the idea is that you take the location and that tells you
Right.
how far,
And-
that gives you your L.
Right, and I can find I know the energy resolution. I can't remember the vertex resolution, but it's tiny. It's really tiny.
Okay, so you get your LO over E event by event.
Right, event by event.
Is it crazy to think about a different shape detector?
Well, I needed to fit, so I had a paradigm, one of which didn't include enough money to build a different shaped detector. But if you find me an existing different shaped detector, I'm happy to discuss it with you. So if you're thinking about, for
Just
example,
thinking something closer to like the, the forward type detectors that you have.
so this is set up so that forward points backward from the detector. So see the beamline come along? And we put all the forward events going this direction because that isotope decay is isotropic. But the neutrons, the fast neutrons are coming off in that direction mostly to fill that room.
I'm just, your solid angle of a cylinder is in some sense, it's a funny match to the solid angle from your source.
You want to be as close to the detector as you possibly can. That's absolutely true. And the very best way to do it would be if you could actually run it down and have your sleeve inside. But we have enough trouble with
So that
could be
thinking about it, more cone-like or something, I don't know.
Yeah. Well, we can talk about more.
Yeah.
I'm open to ideas.
Yeah.
This is, by the way, meant to be a first generation design too. We can keep building these because the accelerator is very modular, so it's easy to do.
So Janet, I have a question. So has anyone looked into the neutrino trident process, such IsoDAR?
For not really, no, not yet. I thought that was actually well understood from LS&D, but I don't know.
No, but actually neutrino trident through the new mediators and all this stuff. So by
Okay,
10^24 POT, I think would be also dark matter.
sure, yeah. I'm really happy to talk to you. This is why I'm giving this talk, so that makes me a very happy person. Let me get back to where I was real quick. Yeah, here. Okay. So there's a lot of new that is going into this. The whole design of the target is new, right? That whole concept is really very state of the art of using the lithium, bathing it and so forth. I don't have time to talk about all of that, so I'm going to talk about only one piece of what's really new, which is the accelerator that is driving this, okay? And I'm interested in talking about this both because I have accelerator physicists in the audience. I also, though, want to speak to this to the people who are the theorists here and also the experimentalists. And I want to do this for a reason. Tiny little lecture, okay? It is just really true that most particle physicists start thinking about their experiments from, say, the target where the particles that they're interested in are produced onward. And they give very little thought to what actually delivered their beam to them, okay? But there's an enormous amount of art, there's an enormous amount of interesting physics, and also there's an enormous amount of physics that matters downstream that you have to be very careful of. And so it is really worth spending some time understanding your accelerator. So that's my tiny little lecture. I do want to say, if it were as simple as simply moving an existing accelerator underground, we would have done this already long ago. Okay, it isn't that novel of an idea. Other people must have thought a little bit about this. So what do we seek in an accelerator? We seek small size because it needs to fit underground. It must be easily broken into 10-ton parts because we have to bring it down that curvy little road in underground. I'd rather have it not be superconducting. You can have cryogens underground, but it's a real problem. You really have to watch out for ODH. I'd like it to be low maintenance for ease of running underground, at least an 80% uptime, producing 10 milliampere protons to get the rate we aim for. That is a lot of protons. And it's 60 MeV to get the rates we aim for also. And I want a relatively large beam diameter. Okay, I don't really mind if my neutrino source is relatively large on the 20 centimeter scale of where it's being produced, given the distance that it travels into the detector. So what I really want is I want to make sure that my power per centimeter squared on target is not something which will destroy the target, okay? Power matters, and it's 600 kilowatts that we're talking about, so it is a high power, but we can spread it out over this 20 centimeter target. And I want it to be low cost because let's be realistic about getting projects through today. Okay, that is crucial. So we found the best solution was a novel high power compact cyclotron. So that brings me to cyclotrons. And so I just want to give a quick cyclotrons 101 to people. Most of you here should know what cyclotrons are because you have a beautiful cyclotron facility, but just in case, I'm going to go ahead and give you a brief review again. These are the pictures from E.O. Lawrence, actually, of the cyclotron that he originally designed. And it's what you learn about in your first electromagnetics class. You know that you can get circular motion of a particle in a magnetic field. So what you do is you have a dipole magnet, a pole piece above, whole piece below, and you start out with your original cyclotron with flat faces between this. And so you put in your particle and you give it a little nudge and it starts going in circles. Well, what happens is that you keep adding energy to your particle through a radio frequency oscillator, then some of the particles will manage to catch the RF wave and surf along. Now, it's only a small number of your particles. Most of them crash out, as most surfers crash out. But some of the electrons manage to get pushed along with an RF wave. So you push them along with an RF wave, and then you let them coast for a little bit, and then they pick up the next wave, and they keep going in this cyclotron. So you're keeping your magnetic field the same, and you're changing your RF as you go along. And what happens is your particles move further and further out toward the edge until you're ready to get them out. An important point I want you to notice is as they make a turn, which is one complete cycle, the turns get closer and closer together, okay? And that's going to be an issue that we're going to come up with, talk more about. That was the first cyclotron ever invented, and it's really cute. You can hold it in your hand. It's an adorable little cyclotron. But easily you get away from something that is quite that simple, okay? Even if you get to relativistic energies, you start running into issues with one where you have fixed your B field and you're changing your RF. So what you would like to do is you would like to build a cyclotron where you can keep the RF the same and you vary the magnetic field. So instead of having flat faces of your magnet, you have what's called hills. Those are the ones that are close together. And valleys, which are very convenient places to put your Ds, your accelerating devices. And what this allows you to do, not only addressing the relativistic issues, but it allows you to put in many bunches at once. With the original cyclotron, you put in a bunch, you rotate it up, out it goes, and then you put in another one, you bring it up. With this one, you can put in a bunch, let it go, next bunch comes along and follows, and so you can have a train of bunches in this. What I'm showing you here is called a compact cyclotron, which means that there is a single coil around the top piece of iron and also a single coil around the bottom piece of iron. So it's a single monolithic coil. And I'm showing you a conventional magnet. That is what we've decided to use, not a superconducting magnet, which makes it larger, but it actually makes it easier to do this underground. We need a much higher beam current than commercial cyclotrons that are out there. So here is the specs for IsoDAR, and here are two cyclotrons that are pretty much the state of the commercial art at the moment from IBA, who are our close collaborators in all of this. And you see that here's the 10 milliamps that we want, and here's what IBA cyclotrons are producing at the moment. So we're talking about an order of magnitude more current than the commercial cyclotrons that are available. Oops. So what's the big problem? Why don't you just stuff in more protons, right? Everything should be fine. Well, your problem comes from the fact that these turns are getting narrower and narrower as you're going out to the outer edge. And any bunch of beams that you have, a beam bunch that you have that's been surfing along on your RF is going to have some tails to it. And so if you think about that in space and you think about, say, the axial position here and the radial position there, here are my bunches, and there's a little bit of beam in between these bunches, right? And you don't want that to interfere because that will cause activation in your machine. And also, you're going to need to get this beam out of the machine once you get it to the highest energy. So what you do is you give it a little electrostatic kick, but that means you have to put in an electrostatic septum. And so you don't want to have those particles hit your septum and kill it. It will basically just boil off, make pock marks. All right, so can we invent a new cyclotron that solves this? The answer is yes. And the person who is really the person who developed all of these ideas is Daniel Linklater, so I want to give him a lot of credit for what is going on here. He won the Hogel-Kim Prize for this. So the accelerator community is really buying into this. It's been a long road where we've been working on convincing them. So at its simplest, what we want to do is the following, okay? And we want to do this at very high intensity. We want to produce the ions to accelerate. We want to collect the ions into bunches. We want to bring the bunches into the cyclotron. We want to enforce good behavior of that bunch. And what I mean by that, I'll get to in a minute, okay? But I want to keep my bunches under control. Then I want to accelerate to the energy that I'm interested in, and I want to extract the beam. I'm going to do this with 3 secrets, okay? The first is this use of the H2+ that I told you about. The second is to bring the beam in using a different kind of an accelerator. It's called an RFQ, which is a way of injecting into a compact cyclotron that has not been done before. And then I want to introduce you to this idea called vortex motion, which is really going to be the secret of the whole thing. I want to tell you that from this line up, that's where all the art of what we have developed is. Once you get those bunches under control, you're really just accelerating the energy you want and extracting it using very common techniques. So starting out with H2+. H2+ alleviates an effect which is called space charge. And one way to think about this is you just get 2 units of charge, 2 protons, for the price of 1 charge. And what you do is you connect them together with an electron, okay? You can break that apart very easily after you've extracted your beam to get your proton beam. So that makes it easier to do many, many, many things in this cyclotron. Bringing the beam from the ion source to this RFQ accelerator, bringing the beam from the RFQ accelerator into the cyclotron. It does have a slight drawback. You now are accelerating essentially 2 protons plus a massive electron, but that's really small. And that means you have what's called a higher rigidity. It is harder to bend. And so you need a bigger cyclotron. And we had to think about that a lot because we're going underground. So are we willing to use that extra space? And we decided the answer was yes. There are many ways to produce ions. You mostly here are using ECR ion sources. We use something which is called a multi-cusp ion source. So it's a different device. The reason why we use this device is because you see that you can produce a lot of H2+ with very little of other kinds of ions that you are not interested in. But the fact is that PCRs are barn burners. And we can figure out how to get rid of these extra things if we need it. This was just a matter of finesse. I would describe it as finesse. But we have built an ion source and it's working very nicely. And we're now moving forward to building a 2nd generation of it. The next thing we need to do is we need to collect the ions into bunches, okay? If we just send a continuous stream of ions into our cyclotron, only the ones that are sitting right here are actually on Earth, right? And we lose all of the others. And common bunchers that are out there right now bunch about 15% efficiency, something like that. And we wanted 80–90% efficiency so that we don't have to run our ion source so hard. So as a result, we have to really think this through. So this is why we introduced this idea of using a radio frequency quadrupole for direct injection. And I just want to say that for axially injected machines, RFQs have been used before, but for the compact machines, they have not. So let me talk a little bit about why RFQs are great. They accelerate, they separate your species, they focus, they bunch. All of that is terrific, but really the only thing we really want our RFQ to do is bunch. We have a little bit of acceleration, but mostly we are interested in the bunching. And here's the RFQ. It's going to be coming in from the top. There's your ion source up there, and here's the RFQ coming down. Our RFQ is a very unusual design, okay? And that is because we actually have to have it match the cyclotron frequency. We want it to be writing the right wave by the time you're done. So we use something which is called a split coaxial design. It has alternating voltage on the vanes. It gives it a little bit of a longitudinal dependence to the electric field. It allows you to do longitudinal bunching because of that. And so all of that's a lot of words. So let me just show you what it actually does. So here you have your continuous beam coming in. So you're looking at, this is looking sideways and this is looking down from the top. So the continuous beam coming in, the RFQ starts to do its job. It's bunching, bunching, bunching. Look at how great it bunches. Oh, something happened there. What happened? It's the end of the RFQ. So it did a great job right until you got to the end of your RFQ, okay? And once it's there, the beam starts to debunch again. So that tells you partly what our next step is going to be. We're gonna need to bring the bunches into the cyclotron, and we're gonna have to do it fast, okay? Before everything debunches. So the way it's gonna work, you bring a beam into a cyclotron, a compact cyclotron, through something called a spiral inflector. It electrostatically bends your particles so that they were coming down this way, they curve around, and then they end up in the plane in which you want to have them accelerate. And you want to get from this RFQ system to this first accelerating cavity as fast as you possibly can. And so our RFQ system comes all the way down to right next to the spiral inflector. Okay. I've got now particles into my cyclotron. They've started to go around turns, okay? They're even in bunches and they're surfing along. So now I want them to behave as they go around. And that is where vortex motion comes in. And this is, I think, one of the most intellectually interesting things about what it is that we have done. So it turns out that vortex motion was a complete surprise to the accelerator community. They were trying to incrementally go from low intensities to high intensities, incrementally up and up and up, especially at PSI. And PSI just kept forcing it. And then when they got to 2 milliamps, suddenly, boom, everything started working. And suddenly they were able to make their intensity go up. They've been up to 3 milliamps now. And the reason why that happens is because it turns out that if you think about how things go around in the cyclotron, it's traveling in a curve in its local frame. And so what happens is that if you have a lot of charge that's pushing outward as hard as it can, right, in these directions, as it pushes outward, there's a force in that direction, there's another force coming from the magnetic field, and the whole thing curls up like a cyclone into a little ball. And this was a real surprise. IsoDAR is the first cyclotron to actually be designed to make use of vortex motion. So this just shows you where the different forces are as around the thing that's pushing outward. And you see we start out at turn 0 with kind of an elongated bunch. By turn 5, it's actually starting to really curl up. And at turn 99, which is where we take it out, it's still sitting there as a very nice, compact little beam. Now, to be fair, we also had to do a little bit of collimation to get rid of some of the tails on all of this. And so this looks so clean because we had some collimators. You collimate very early on so that you're not depositing too much energy into your collimators, and you can. All right, it's all pretty standard. Accelerate to the energy you want. The only tricky part here is the fact that we're trying to build a ship in a bottle. So we have to bring our coil down through the tunnels, which sets a length of the width of the coils. And also, this is a mesh that shows you what the cavern looks like. You have to be able to fit in the crane and build the cyclotron underground. And lastly, we need to get the beam out. You extract the beam using a very common device, which is called an electrostatic septum, which is what you see right here. The beam comes in between two pieces of metal. So you bump the beam slightly outward, and we have 2 points at which we can bump the beam outward, and we're below our 200 watt limit of losses at that point. We have done an enormous amount of work on this, and we are very, very proud. And we put up originally about a year ago an archive article on this, and we've gone through a whole set of reviews. We have just updated this in response to the reviewers. And so we have this nice preliminary design report. I don't expect you to read all of what I've written here, but I want you to admire that it is basically 76 pages of engineering that we are very proud of. Yeah. And more than that, I want you to realize that it's a family, okay? So what I'm showing you here is IsoDAR, our 60 MeV cyclotron. But I want to remind you that everything from here upward was what was new and novel. Everything below accelerates the energy you want and extract the beam. That's very tunable depending on what it is that you would like to do. So I would like to introduce you to MiniDAR. MiniDAR is a full-scale test of all of the ideas that we have here. But it is a 1.5 MeV per AMU cyclotron. So what's really small is just the cyclotron that you see right here. And I think I said in my talk, you know, that it's important to realize that accelerators don't just appear. So what we really need is a postdoc. Okay, and so I'm really hoping that somebody here at TAMU might be interested in a postdoc position working on building this. I think this is a really exciting paper. Right. Another thing that's really neat, once you realize you have a family of these cyclotrons, is that this is actually very valuable to wider communities, what we have done. So this is basic science with direct, immediate relevance. Our cyclotron research is partially funded by grants specifically for applications, for medical isotope production, for a prototypical fast neutron source, and we also just got a grant for using a 60 MeV machine as an injector to a larger cyclotron for transmutation of nuclear waste. So this just gives you an idea of why IsoDAR is very important. This is an example of how the level that actinium-225, which is a alpha source, can actually address issues of cancer. This is a body that's riddled with cancer, and then the treatment by actinium-225. You produce actinium-225 with a 60 MeV accelerator. So it's really good for anything that is a long half-life and low cross-section area. And we have a Nature article on this if you would want to read more about our medical isotope production. The biggest problem with the medical isotope production is that what we have is a barn burner, right? We have a very, very intense beam. And that is not how targets for medical isotopes are designed at the moment. And I really believe that it is possible to design targets that will work for this, but it would also be nice to just be able to use the targets you have or do it incrementally. So one of the reasons why we are excited about extracting H2+, which you then strip off an electron to get your proton beam, is because you can take a stripping foil and you can stick it just barely into the beam, a tiny amount, and off will come protons that you can bend away. And you can keep doing that over and over to many, many stations. So it's a bit wasteful. You will lose some that way, but you will gain much more because of the high intensity. There's more. Any kind of machine like this, any kind of cyclotron with minor corrections will accelerate particles, ions with the same mass to charge ratio. So for example, we can accelerate alphas because it has a mass to Q of 2. We can also accelerate deuterons. And deuterons are very interesting, especially if you accelerate them to 40 MeV, because when you break them up, you end up with a 14 MeV neutron coming out by the time you are done with it. And that's of special interest both for medical isotope production. Some ideas of how to produce actinium-225 require a neutron bath at about 14 MeV. And also for fusion materials testing. And in particular, we were asked to say how well our accelerators can do compared to what the world is planning to use as a prototypical neutron device. It's called IFMIF. Well, it's now called IFMIF Lite. It started out as IFMIF. It got reduced down to IFMIF Lite. And so we looked into this, and it turns out what you would do is you would use 10 of our cyclotrons. You would actually use 12. 2 of them would be off at all times. You would be alternating which ones are getting maintenance so that you have 10 on at all times. And you can produce a lot more milliamps per $1 million that you put into the system with these cyclotrons. So if you want to learn about that, there is an article on that. And lastly, very interestingly, we were just funded for a group that is very interested in looking at transmutation of nuclear waste. So this machine, our IsoDAR 60 MeV machine, would be used as an injector into a larger cyclotron. This is commonly done. It's done at your cyclotron facility. And so this injector would then go into a larger cyclotron up to 800 MeV and be used for transmutation of nuclear waste. And it shows how things go in complete circles, because originally, when we first started out with this, it wasn't the premise that I gave you. The premise was, could we do CP violation much, much cheaper than Dune? And we had worked out a whole system called Daedalus, which had this little injector cyclotron, right? And then we realized there was so much we could do with that injector cyclotron. So everything has just come full circle around So if nothing else, I want to convince students that keep your ideas, even if they don't work out, they may come back and work out just fine. Also, this is really different for me. I have never been relevant before. I can be entertaining, I can convince people that the physics that I do is exciting, but I've never actually been relevant. It's really quite nice. I've covered a lot of material here. We have an IsoDAR website where we select publications, and they're kind of randomly selected, but when I looked at them yesterday, I noticed that the Axion one was the one that came up for being shouted out here. So this is the one I did with Bhaskar. Actually, there's 78 more besides these on here. We are extremely prolific in writing papers, if nothing else. And so I hope I've convinced you that IsoDAR is something really different for particle physics experimentalists, for particle theorists, the accelerator community, and for wider communities. And thanks for having me back again. I keep coming back. They're hard to get rid of. So thank you very much. And see, I'm not over time because I've only spoken for 5 minutes. Other questions?
So what is the price tag for this system?
Okay, the whole system, which also includes.
No, I'm talking
sleep,
about IsoDAR exclusively, IsoDAR 60 MeV, right?
just for the cyclotron.
Just for the
The
site.
cyclotron, so we're working with IBA, and the cost estimate from IBA is 20 million for the first cyclotron. And then it'll be cheaper when they're starting to make more cyclotrons. So we are very interested in partners,
20 million?
20 million. Yeah, it's not that different.
That's almost for free, essentially.
Oh, well, I think so. I love you. That's great. So basically, it's not that different from their C series that they have been developing. It has these special tweaks to it of the RFQ, which is not a very expensive device, of running the H2 plus. It's a little bit larger than their C70 cyclotron is, but it isn't very, very different from that. So it allows us. We're even planning to use their D designs, their RF.
And the focusing, so is there an option to focus it more because you said it's like 20 centimeters?
Oh, we're doing that on purpose. We don't want to blow up the target.
Yeah,
Yes,
I understand,
you
but
could focus the beam more, right? So what it is, we're bringing it out as H2 plus, and then we're stripping it, and then we're taking it along a beam line that's 30 meters long. And we're purposefully allowing it to become larger as it gets there. So yeah, you can definitely focus it down. It'll never be like a LINAC.
sure.
You know, as I said, LINACs are very nice, but they're too nice for us. We don't want to blow holes in things. So. Nice to see you, by the way.
Pardon?
Nice to see you. Hi.
You too. Have you, has anyone put the vortex motion dimension of this into experimental test in a cyclotron?
Okay, so no, and that's what MiniDAR is about. And that's why I think MiniDAR is going to be so exciting. So the whole purpose of MiniDAR is to bring this through turn 5, where we show the onset of the vortex motion. So one thing that we have done is there's many measurements of this vortex motion coming out of PSI. And so we've written a lot of simulations that reproduce what PSI has been seeing and using that for this. But the reason why I think this is really a great, so I'm just going to do another pitch for the postdoc position. The reason why I think it's so exciting is because I think if we show you can design with vortex motion in mind, it opens up an enormous amount. I really think it does. Yeah. And I'll get back to you, okay?
You mentioned ODH being a concern. Is everything just going to be water cooled at that point then?
Actually,
in
you
the
know, the target itself is D2O cooled, but most of it is just regular water cooled. Yeah. But we use D2O inside of the target because we are producing a lot of neutrons and we want to not lose those neutrons to capture on H2O. So it's not very many liters. And it's well combined. Yeah. Mhm.
The use of H2 plus has the benefit for you that you can, you have more agility for extracting and for doing partial stripping and things of that
Right.
sort outside. It would seem to me to be going very much in the wrong direction for everything that happens in those first 5 terms. in the RFQ and in the first 5 turns. Space charge tune shift, it goes like 1/beta squared.
Mm-hmm.
The step in particle velocity beta with the energy you can add with an RF cavity goes as 1/beta. So you have a
But we
factor
do-
beta cubed in your face when you try to push this for transporting and accelerating high current.
Yeah, so we don't actually really accelerate with the RFQ. The point of the RFQ is almost entirely bunching. So
You accelerate in the first 5 turns of the cyclotron.
we do accelerate in the first 5 turns of the cyclotron, absolutely. And so there, we actually do have to deal with the fact that we're pushing, if the rigidity is harder, that we're pushing particle that is harder. The thing about it is controlling the vortex motion. We want it to be at a level that's on the order of 5 electrical milliamps or so, which is very close to where all the PSI work was.
Mm.
And so we were trading that off. And so that's part of the reason why we're doing this. It is also true, though, that originally we were very interested in the question of whether we wanted to do stripping. And what the H2 Plus allows us to do that's very important in extraction is, let's say we've got it wrong and there's more tails than we actually thought as we get to that septum. Then what you do is you put in a stripping foil a little bit upstream that cuts onto those tails. You strip those into protons. They go flying out of your machine in some other direction because they're protons now. So they go across and exit. And now what you have is you have a clean H2 plus beam coming out. So there's a lot of nice reasons to use the H2 plus. There's also drawbacks. There's no question about it. So we did a lot of weighing of both of those. Yeah.
I have 2 questions. One of them is it just conventional RF sinusoidal, or are you thinking of any other time structure like flat topping or something?
No, we're just going to use a regular sinusoidal structure. We are thinking about chopping beam.
Yes.
There's a couple of reasons to chop. First of all, we have to have a beam chopper at the beginning because you see, we have to have our bunches be as intense or we won't get the vortex motion. So we can't go down in intensity that way to bring things up. So we have to chop instead. But also because that makes an interesting beam structure further down if we wanted to use it. It's a little tricky because the lithium 8 has an 800 millisecond lifetime. So
that was the second question I was going to ask is, it sounds like you're not going to be able to do something of kind of cutting out the beam on the injection to put a larger pulse in to look for the prompt versus kind of delayed structure in the detector.
that's right. You would go way down in intensity because you would chop a lot of beam out in between. You would drop way down in intensity.
But if there was something with a shorter lifetime that could be made by
That's
neutron
right.
capture, this would be possible. Yeah.
This sleeve was made for the premise that we put forward, but there are other kinds of things that you could do. A group out there has come up with the idea of actually doing a 15 MeV machine on aluminum, and that turns out to produce I can't remember what gets produced from it, but there's a really nice neutrino beam that you get from it. But it's got a lifetime that is much shorter. And so as a result, bunching would actually matter for that. I have to look that up. That would be what you would want to do if you wanted to run at Dune. Because Dune is argon and has no hydrogen in it. You wouldn't get any inverse beta decay. So unless you're interested in only scattering off of the electrons, you would want to have this ability to run with neutrinos.
I think it would be nice to put a 7th detector inside your IBD detector.
We would be very glad to have you come
So you
and
don't
bring
waste
your
any more
detector. Let me just show you. There is plenty of space, actually. So what we wanted to do is we wanted to have the cyclotron very far away from the target for Alara. And we wanted to do this, and it turned out because of where the tunnels were already in the mine, that it made a lot of sense for us to have this 30-meter distance along here. It's not hard to bring a beam 30 meters at 60 MeV. But if you would like to sit right in here, we have space in this room. You can just put your thing right there and we would be very happy. We would welcome you.
Yeah, it sounds like a good opportunity.
Okay, well, thank you. I appreciate you listening to me. It's